thanks a lot for the invitation, and thanks for putting together this this nice conference. In this talk, I will be talking about a set of topics which are based on the following set of papers, namely some paper from myself from last fall, and then two works together with Brice Bastien and Damian van der Heijsteek. And I will also spend some time discussing upcoming work with Erik Blauschin and Damian van der Heijsteek, and three well-known mathematicians, Christian Schnell, Ben Bakker, and Jakob Zimmermann. So let's get started. I think it's good to first place my topic into kind of what kind of direction I want to go to. Namely, I want to talk about aspects of the so-called swampland program. And what is the idea of this program? Well, one wants to identify general principles that have to be satisfied in an effective theory to be compatible with quantum gravity. So I give you an effective theory, which might be somewhere in this blob here. And then there is a subset of these effective theories which are consistent with quantum gravity, and these we call the landscape. And then there might be other effective theories which seem to be consistent, but they are actually not, because if you couple them to quantum gravity, they're just kind of some hidden inconsistencies. So that's the direction I want to go in. And let me now be a little bit more precise. In this talk, I focus mostly on field spaces and scalar potentials in effective theories. So I will consider an effective theory at some cutoff scale lambda, and then this effective theory, it might have some scalar fields, which I call phi here, and some field space M. Yeah, the M will always be the kind of the scalar field space. And these scalar fields, they might be constrained by a scalar potential V of phi, which you can think of as a map from this field space M to the real line. And one of the questions you might ask, and of course that was something which was studied recently a lot, is which field spaces M can appear in the landscape? Well, this was not studied that much, but the question was asked which scalar potentials V of phi can be arising from consistently with quantum gravity. Yeah. Of course, these two questions are related when we lower the cutoff. Namely, we can start with an effective theory which has some field space M, and then we can lower the cutoff. And then it might be that some of the fields are now too heavy to be still part of the effective theory, and we rather should integrate them out. And if we integrate them out, then the resulting field space M1 could be of lower dimension. Right? The previous one was one-dimensional, now the previous one was two-dimensional, now it's one-dimensional. And there could be also many different ways of looking at this previous potential and kind of reducing to this theory with lower cutoff. And you might even lower the cutoff even further, and then you have to integrate out even more fields. Maybe you just have to keep the massless fields if the cutoff is sufficiently low. And then your new field space might be just point-like. So your fields are actually stabilized. So they are set to their actual vacuum value. And maybe there's no flat direction remaining in some cases, or in other cases, there might be a flat direction remaining. So now, if you think about this picture, you might ask, well, if I ask about string theory or quantum gravity in general, we can ask, is the number of distinct effective theories compatible with quantum gravity finite? Of course, this is long part of the string phenomenology program. I think I don't have to explain why this is the case in detail, because it's clear that if you have infinitely many choices, then kind of a statistical arguments, for example, make little sense, or any precise statement about I checked something in 3 or 4 cases is not so relevant if you have infinitely many cases which you would have to check. And so it's an important question for a long time, and there have been a lot of works on this question, including a much recent activity where it was studied the finiteness of spectra, rungs of gauge groups, and so on. In this talk, I will end up in the last part. Well, in the middle of this talk, I will indicate a non-trivial finiteness proof. So I will exactly address one of these finiteness questions, and I will argue that one can mathematically prove finiteness. And then, guided by this success, I will claim at the last part of the talk that finiteness should be promoted to a universal principle to constrain effective theories. So why is that exciting? Well, finiteness is something which is independent of supersymmetry. This principle which I mentioned, it has nothing to do with holomorphicity and all of these things which you might question as someone who says, well, supersymmetry has not been detected and is not a relevant concept for many of these questions. So this is the motivation, the few words of motivation. Now let me outline my talk. In the first part, I will kind of start to get an intuition, what should this finiteness structure be, right? And the way how I do this is I will talk about the complex structure moduli space and flux vacuum. So this is something which has been studied for quite some time, and we made some nice progress, I believe, in the last couple of years. And I want to tell you what are the lessons about the complex structure moduli space and flux vacua that we learned in our study. And to give you an upshot of the statement is, well, the statement is that scalar field spaces and scalar potentials which arise in type 2B flux compactifications are remarkably constrained. So they're by no means random potentials or anything like this. Yeah, so they are very constrained, and I will try to explain what these constraints are and then abstract them into general constraints. Then these remarkable constraints on the scalar potentials, they allow us to actually show the finiteness of flux vacua, of self-dual flux vacua. And I will already give you some hints on the structure of the vacuum landscape in flux compactification. And if you look at the proofs, it's quite amazing that the structure is, or the information is just enough to ensure finiteness. Yeah. So it doesn't have to be there. It's not a simple argument. It's a very non-trivial argument, but it just works out fine. And finally, I want to tell you about the tameness of the landscape and promote it into a principle. And for this part, I will have to introduce you yet another quite involved mathematical machinery, but it's a very fascinating machinery. I'm also not a full expert on these things, but I'm learning every day more on it. And this is actually the theory of O-minimal structure on tame topology. And this is also what we used in this finiteness proof. Okay, so let's get started. Flux compactification, some lessons that we learned over the years. So let me first explain what are flux compactifications. I believe that many of you have seen it, so I can be very brief, and we also heard about that yesterday. So we study type 2b flux compactifications. We switch on some background fluxes, which are integral three forms, and we have a tadpole constraint, which is like this. Now, as you might know, these three forms can be combined into a complex flux with the dilaton axion tau, and then the vacuum condition is the following, namely that the Hodge star of G3 is I times G3. So the flux has to be imaginary self-dual in the vacuum, right? So this turns out to be also a consistency conditions onto the 10-dimensional background if one studies type 2b orientifold compactifications. The nice thing is that this kind of condition and this kind of setting actually lifts naturally to F theory. In fact, that's where we should study it because it's so much more powerful to just go one dimension up. And in F theory, the flux is not a complex flux, but a real flux. So G4 is actually itself integrally quantized or half integrally quantized. And it's also constrained by a tadpole condition of this form. The vacuum condition takes this form, namely that the Hodge star on G4 is equal to G4, right? So this is the same condition like this, but in an F theory setting. And we want to study these flux vacua in the following. Why do we want to do that? Well, because this setting is really well justified, right? So this is a very well studied set of n equals to 0 and 1 vacua and it is known from examples that some complex structure moduli can be fixed from this. The back reaction is under control, higher derivative corrections can be consistently included. And I think it's fair to say there is no minimally supersymmetric setting which has been studied to this much extent, right? So this is our motivation, or that is our setting. And so why, when I say it has been studied a lot, that means mostly in examples, but so why is it complicated to get general insights about this? Well, you have seen, I talked about this flux vacuum condition, and there the Hodge star appeared. And this Hodge star changes over the complex structure moduli space and the complex structure moduli space, but also the functional dependence of the Hodge star on the complex structure moduli is very, very complicated in general, right? So what people did is they said, well, but then let's use the fact that the effective theory is actually supersymmetric, that it's n equals 1 supersymmetric. So what does that mean? That means that we can formulate the scalar potential, but everything else in the theory via a scalar potential and a superpotential, yeah, and a gauge coupling function. And this scalar potential and superpotentials are now defined in terms of this unique d,0 form on the Calabi-Yau d-fold, so 3,0 form on Calabi-Yau threefolds, and this flux GD where G3 was complex and G4 was real. And then the vacuum condition is actually just a condition that the F terms vanish, right? At least the F terms for the complex structure moduli and the dilaton axion in n equals to in Calabi-Yau threefolds, right? In Calabi-Yau fourfolds, it's just complex structure moduli. So this is the same. If you evaluate this, this is the same condition as having self-dual fluxes. So why does that seem to be easier? And in some sense it is, namely everything is now formulated in terms of the so-called periods of omega, namely the integral of omega over 3 or 4 cycles. These are now holomorphic functions or sections, and they are constrained by holomorphicity. Yeah. Nevertheless, they are complicated transcendental function, and they are hard to compute, even for examples. Yeah, they are very hard to compute in many cases. And it's even harder to see any properties by staring at them. Yeah. But that's not the way how we want to proceed. We don't want to go through specific examples, but we want to take general conclusions about the moduli space. And the way how we will do it is we say, well, the complex structure moduli space actually has a non-trivial structure, and it has boundaries, and therefore it has asymptotic regions. And so the minimal hope which we can have is to learn something about the periods in these asymptotic regions. Let me give an example. So for the moduli space, for the mirror quintic, is just a two-sphere with some special points, and these special points include, for example, the conifold point or the large complex structure point, and these are exactly these sort of boundaries I'm talking about. And the near boundary regions, where we can hope to study our system in general, not for specific examples, are then these kind of regions near the conifold or near the large complex structure. Maybe it's interesting to point out that we are talking about holomorphic functions, so these regions will be these places where the holomorphic functions have singularities, and this is actually the important information about the holomorphic function. That's one of the important informations about holomorphic functions. Now you might say, why are we interested in asymptotic regimes? Well, in string compactifications, we work always in an asymptotic regime. For example, we work in the large volume regime to gain control, or most of the time we work in the large volume regime. And by mirror symmetry, this is exactly the dual of this region here. So if we learn something about the dual of this region, that's always useful for our study of string compactifications. Now, unfortunately, the picture is not quite as simple as it is for the mirror quintic, but in general, the boundaries of the moduli space can form a really difficult, complicated net of intersecting subsets of the moduli space. And I give you here this example, and you see the conifold locus has some very non-trivial intersection with other boundary loci and so on. So in higher dimensions, we expect that this study will be orders of magnitude more complicated. And in fact, that's one of the main lessons you also can take home from my talk, is that when you learn something from a one-dimensional case, if you go to higher dimensions, it will be much, much more complicated. So now we want to get a systematic understanding of these asymptotic regions without going through examples, identify flux vacua. Maybe we can also test conjectures. And in fact, that's what many people did also exactly in this setting or a similar setting. And I refer you to some excellent reviews on this, and also some papers which maybe have some of the closest overlap with what I'm going to say in the following. So what kind of technique did we use in order to kind of get these general results? Well, we developed tools in asymptotic Hodge theory and applied them to test conjectures, and in the finiteness case, we applied them to prove conjectures, to prove a conjecture. This is already started some time ago, as you might know, but I should alert you that only more recently we kind of get a full understanding how powerful this actually is, and I hope I will convince you of this in the first part of my talk, namely in the specific lessons which we learned. Yeah. So let me first say the first lesson, quickly sketch this. Well, first of all, we understood that on each of these boundaries, there is a PQ decomposition, and a decomposition into SL2C to the n representations. So for every boundary, you can associate kind of something like a Hodge decomposition in PQ types and an SL2 to the n group and its representations. And the representations which will appear on the boundary kind of is specific to the boundary in complex structure moduli space. And this you can do for every boundary which occurs. Yeah. And the codimension n boundary gives you an SL2 to the n. Yeah. So let me just explain this quickly for a Calabi-Yau threefold, where I send one modulus to the boundary, then there's just a single SL2. Then there is on the boundary a PQ decomposition like this. This you have seen before, but I alert you, this is now a very non-trivial statement, because on the boundary, the manifold is wildly singular, right? These boundaries are the conifold point. The boundary is the large complex structure point. At the large complex structure point, there is a PQ decomposition. And then there is also an SL2 decomposition where we can introduce SL2 spins and highest spins. So this is something which we know very well from physics, and then classifying these allowed representations allows you to classify the boundary. So we get, for higher dimensional cases, we get multiple SL2 spins, and in fact, you can assign really multiple spins to one for one boundary. So I mentioned it already. This gives you a classification of boundaries using SL2 representation theory and some positivity constraints. So just to kind of sketch a little bit how what is kind of the outcome of this, you get for one modulus cases, you get 4 types, so mild degenerations, and then 3 principal times of what kind of can happen at a singular point in this complex structure moduli space. In the 2 moduli case, it gets already much more complicated, and there are in 16 non-trivial cases, and then there are the mild degenerations, so similar to this, plus the 1 modulus cases. So in total, one has something like 20 cases. Yeah, and just to stress this once more, whenever you do any computation in any example, it has to fall into one of these cases. Yeah, so there's no way out. And in fact, I can assign some recent papers. I can say what kind of cases they have studied. Yeah, so these cases have been studied here. These are the Seiberg-Witten theories, which also have appeared in some recent papers by Timo and collaborators. And then the large complex structure cases, of course, all appear in the Kreuzer-Skake list. So every case you find, you can put into this list. Okay, and don't worry about the names; these are just labels to these various boundaries. Now, the second lesson we learned is that it can be useful to directly approximate the Hodge star near the boundary. And in fact, the approximation of the Hodge star is given by the SL2 spins. Yeah, so this is another result from asymptotic Hodge theory, namely that the Hodge star of a form actually can be approximated in this way if you go to this limit where these y's are very large, so they are close to this boundary point. This is a very crude approximation, but it's extremely easy to handle, because you're just dealing with algebraic polynomial equations. Yeah, so if you're looking for vacua, as I will discuss later on, you just have to solve polynomial equations, and that's for a computer, that's very easy. Yeah. Now, more recently, we understood that this technique is even more powerful, namely that in the asymptotic regimes, you can even reconstruct not only the leading Hodge star, but the also subleading corrections to the Hodge star, and also the periods themselves. Yeah, and this can be done solely from the boundary data. So you specify some data to the boundary, specifying the boundary, and then you can use this to reconstruct the periods into the bulk. Yeah. So what kind of data you need? You need the SL2 data, which I already told you they are classified. And in fact, you can write down simple normal forms. And what you then also need is some additional information, which we call phase operators. They have some specific meaning in Hodge theory. And we can make a general ansatz for them because we know their properties. And if you put all of this together, you can reconstruct the periods near the boundary. So this is mathematically reasonably involved. But what you find then is that every period which you get close to this boundary has a polynomial and some exponential instanton corrections or essential exponential corrections. We call them instantons just because they remind you of instantons. This is just geometric. Everything is geometric here. So in fact, at most boundaries, you find these essential exponential corrections, and you need to include them because they are, for example, required to ensure the non-degeneracy of the moduli metric. So if you're not a large complex structure, it's very crucial to realize that you cannot work just with polynomials in the periods. You need to include exponential corrections, and you can compute them using these Hodge theory techniques. Let me show you some examples. So this is the one, these are the kind of the general models which you find using these Hodge theory techniques. In the one modulus case, there are these finite distance case, which is, if you look closely, are the conifold periods. Then in the type 2 cases, the infinite distance cases, then you find these periods, and then you can imagine that if you go to higher dimensional moduli spaces, this gets really complicated. But the remarkable thing is, without using examples, you can do it. Yeah, so there is an algorithm to do it, and this is the result which you find. So for each boundary, you can now write down the periods near this boundary in a specific form. So here I write down the ones for the type 2 boundaries. So this is just a name. The Seiberg-Witten boundaries. Now you might say, well, but what is this useful for? Well, first of all, I told you it's essential instantons, so you need them. Yeah, you cannot get away without using them because everything will be kind of degenerate and singular. So but there are also practical applications, as we showed in the paper which appeared on Monday. Namely, one can construct vacua with exponentially small superpotential. And this has been done before, and there was a nice algorithm suggested in these papers here, especially the first paper, and they carried this out near the large complex structure and the conifold point. And what we succeeded in is kind of to explaining now how one conceptually understands this construction in asymptotic Hodge theory near every boundary, not just in these specific cases. And we also show we construct new vacua using essential instantons. In fact, one should say that in Hodge theory, this kind of settings where you have these exponentially small quantities, they have been studied, and they called it the extended locus of Hodge classes. In either case, in any case, the strategy now to construct such vacua is the following. You take your split of your periods into these polynomial pieces and these essential instanton corrections. You also split the Kähler potential and the superpotential accordingly. Remember, we can compute them, right? We can construct them explicitly. And then you look for vacua. And the first idea you could have is, well, let's just look for polynomial vacua and then say, what can happen is you get exponential corrections, so you get only exponentially suppressed correction to this story. The fact is that this is not true because derivatives and kind of dropping exponentials does actually not does not exchange. So these essential instantons are essential because if you take derivatives, they actually kind of are important and they become polynomial corrections in the lower level, so to say. So, and that's exactly what happens in these type 2 points in this example, which I showed you the slide of, in these Seiberg-Witten points, and consider this sort of scalar potential, which you get by just plugging in the periods, which I showed you before, and it has an instanton correction. And you see immediately that if you compute the metric from the polynomial piece alone, it is it's just singular. Yeah, the Kähler metric would be singular. So these instanton corrections, these exponential corrections are needed, and therefore we call them metric essential, right? They are needed to ensure the non-degeneracy of the metric. And now we realize that the Kähler potential and also the flux superpotential has these polynomial and exponential corrections. And now we can solve these vacuum conditions, and they in fact become polynomial, right? Because these exponential corrections, if you take the derivatives and you drop over all exponentials, become polynomial equations. And what we then find is that indeed these exponential allow you to find explicitly vacua which have an exponentially small superpotential, but polynomial masses for the moduli. And it's exactly because of these exponential corrections are these metric essential instanton corrections. And in fact, this fits very nicely with the result that the Hodge norm in asymptotic Hodge theory is polynomial. Yeah, and that's how this can work. So despite the fact that there are exponential corrections in the periods, the Hodge star can still have a leading polynomial piece because the exponentials cancel.
Question.
So you see is there a question?
Yeah, sorry for interrupting your flow. I just want to make sure that at least here you call this essential instanton is came from the worksheet, right?
So can you repeat the second part, please?
I mean, and just want to make sure that here the essential instantons came from the worksheet instanton, right?
That's where we picked. That's where we picked the name from. In large complex structure, large volume, there it's indeed these instantons would be kind of worldsheet instantons. The unfortunate thing is that at large volume, there are no essential instantons, as you might know, right? So at large volume, you can just drop the instantons and your metric is still okay. The point is that if you go to other points in moduli space, in complex structure moduli space, where these are just exponential corrections, you cannot drop them. Yeah, so at large complex structure, you can drop them. At other boundaries, at most other boundaries, actually at all other boundaries which we showed, you cannot drop them. Otherwise, you find inconsistencies.
Yeah. Okay, thanks.
Yeah, so remember, we are on the type 2b side, so these are not worldsheet instantons. The mirror would be worldsheet instantons. Okay, and finally, one can kind of make a full story about modular stabilization using these asymptotic Hodge theory techniques. Namely, we can now use the other lessons to study this vacuum condition systematically. I told you already we did this for the small superpotential, but you can now promote this to a kind of an approach to moduli stabilization. So namely, what do? You first study moduli stabilization in this asymptotic regime using the SL2 approximation. So if you go deeper and deeper into the moduli space, this approximation will become more and more crude, like kind of it will fail, there will be corrections. But the closer you go to the boundary, the better it will be behaved. Yeah. But you can do it as a first step, and it's actually quite easy to implement because I told you it's polynomial, right? So a computer can easily do it. The next thing is you can include these exponential correction, these essential exponential corrections. mathematical terms, this is called the nilpotent orbit. And then you can find a refinement of the SL2 vacua. And finally, we don't do that because that's quite involved and you really need examples. Yeah, you can compute the full periods and then you would find the exact vacuum. But these two steps here, the first two, you can do abstractly. Yeah, because they are fully within the framework of asymptotic Hodge theory. But of course, you then have free constants in there, which you can then determine from example to example. There are many interesting things happening in such a moduli stabilization scheme. For example, a flat direction in the SL2 approximation might be stabilized in the second step. Yeah. So this is a very algorithmic approach to stabilize moduli, and it can be done abstractly or for examples, and even for examples, it has favorable numerics as we show in our upcoming paper. And we can implement hierarchies, this I already explained, and it is also works because it's abstract and algebraic. It can also work for a large number of moduli and fluxes. And this is, I believe, a very powerful tool to address the topology conjecture, which was yesterday discussed in Joseph's talk. Okay, so this leaves me at the end of the lessons. Now, I want to spend the rest of the talk to explain how these tools, which we learned from this study, can be useful to actually prove something, namely the finiteness of self-dual flux vacuum. I remind you of the question. This is the question. It's a mathematical question. You want to have integral fluxes which are self-dual and satisfy this topology condition, and we fix the Calabi-Yau manifold for this discussion. So we're not proving finiteness of Calabi-Yau manifolds. There have been evidence for the finiteness of flux choices by Douglas and collaborators in the past, and I don't want to discuss this in detail, but they never really showed it, right? They put out a number and then people thought, oh, this is clear, but it's actually, it was an open question and actually quite surprising to the mathematicians I worked with that this should be true, and now it's shown to be true. So this is a very hard mathematical problem. One cannot stress enough how hard it is, and you will see later on why it is hard a little bit. So first you could think, oh, this is a very simple mathematical problem because, well, the topology conditions and combining it with the self-duality condition, then you write the topology as something positive. So, and this is bounded, so you bound something positive with a number, and so you think of it, this is the flux lattice, and then you draw a circle, and since this is kind of something positive norm, then it's just some circle, and then you just count the number of vacua, and that's the answer, right? So it's obviously finite. The problem is that this is not a statement for a fixed manifold, right? For a fixed manifold, it's trivial, but if I allow the manifold to change shape, then it becomes a highly non-trivial statement. Namely, this Hodge star can degenerate, right? It can develop a singularity, can become arbitrarily small. And if it becomes arbitrarily small, the fluxes appear to be able to become arbitrarily large. Yeah. And so you think, oh, I can put more and more flux. Yeah. But the point is, this is not possible. And the way how to show that it's not possible is you have to control the Hodge star and the periods or the periods, if you want, near the boundaries of the moduli space, because that's the only place where the Hodge star can degenerate. Inside the moduli space, the problem is trivial. And by the way, many of these problems are like this, right? So they are inside the moduli space, they are trivial, but if you go to the boundary, that's where the whole story happens. Yeah. It's about what is the compactification of the modular space. So the first idea would be a direct approach. You show that on every path to every boundary, only finitely many vacua can exist. Yeah. So this would be the first way to do it, and you use the SL2 techniques to do it. Now, this can be done, and in fact, you need the full power of the SL2 asymptotic techniques. And this you can find in my paper from last year. And if you want to understand what's really behind this, I encourage you as a start to read that. I hope it's comprehensive, because you need to acquire a little bit of the, not a little bit, quite a lot of this SL2 asymptotic knowledge. Yeah. But it can be done, and it's really remarkable. You see that all the bits and pieces, they come together precisely such that you can never escape to an infinite amount of vacuum. Unfortunately, and that's, I told you, is one of the lessons, the general story with more moduli is orders of magnitudes more complicated. Yeah. I should mention there is a famous theorem by these famous mathematicians which show this for 2,2 fluxes. Of course, they don't care about fluxes, but they study so-called Hodge classes, which are what we would call 2,2 fluxes, namely integral fluxes which are 2,2. Yeah, and this paper is so famous because it's kind of viewed as the strongest evidence for the Hodge conjecture, and that I tend to always bring this up, but it just is meant to indicate to you that this is not a trivial question, right? These are very, very non-trivial questions. And what do? They are very ingenious people. They use these SL2 techniques for multiple variables and indeed control every path to every boundary, not just for Calabi-Yaus, but in general. But they use holomorphicity in a specific way. And so for them, it's important to have these 2,2 fluxes or P, P forms on a Calabi-Yau P-fold. The general proof is more involved, and it actually uses some recent breakthrough where by Bakker, Klingler, and Zimmermann, which connect Hodge theory, so the things which we discussed, with another mathematical field which is called tame topology. And just to sketch a little bit what they suggested is, what they found, what they proved, is that the period map, so these are the periods which I used, but there is a more fancy formulation of this, is actually has specific properties. First of all, they showed that the place where this period map ends, these kind of quotients, these arithmetic quotients, they have a tame topology. I will indicate in a moment what that is. That the period map is by no means a general map, right? It has holomorphicity properties, but even then it's not general, right? It's a very special map which is tame, yeah. And they use these SL2 techniques to show that. And then they give an alternative proof to this theorem of this famous theorem on Hodge classes. Okay, so what does that mean in like a more physicsy, very rough sense? It's a statement that these arithmetic quotients can be covered by finitely many patches and can be glued together in a nice way, and that the period map is mapping finite sets to finite sets. This is a rough way of thinking about this tameness. So now we can ask, what about the scalar potential, right? And that's exactly the sort of question we want to answer, namely if there are finite many solutions. So finitely many solutions to what? Well, we know that the scalar potential can be written like this, so as an absolute square, and then a self-dual flux actually is a zero of the scalar potential. Yeah. So what we want to show is that there are only finitely many zero sets. That's what we want to prove, right? And that this is non-trivial is because there is an infinite flux lattice, which is appearing here, right? You can pick infinitely many fluxes, and these. So in principle, this is a function which maps an infinite set to an image. Yeah. And what we show in this upcoming work is that in fact this combined thing has this finiteness property preserved if one imposes the tadpole bound. Yeah, so that this is kind of this sort of is also some sort of tame function. Yeah. So what is the statement of the finding is that if you have your moduli space and your flux lattice, then there are only finitely many choices. So you have a choice in the flux lattice, and this might give you a vacuum, which might be point light in the moduli space, or it might be of higher dimension. So there could be one modulus which is unfixed. But the point is, these sets, there's just finitely many sets of this type. So you can have finitely many choices in this lattice, which give you finitely many subspaces of the moduli space. And that's the statement of this finiteness theorem. Now I mentioned a couple of times that this uses kind of this tame topology minimal structure. And so I should tell you in the last, I think I have something like 7-8 minutes. I want to tell you a little bit about the minimal structure of the landscape. So now, so if you are not interested in flux compactification, then you should wake up now. What is the mathematical structure behind this? Well, it's the idea of developing a mathematical framework which somehow respects finiteness properties. Yeah, and it also removes kind of pathologies which occur in an ordinary topology. Yeah, and in fact, this was envisioned in one of Grothendieck's famous essays, in 84, sorry, the German thing, 84, and it's called tame topology. And this led more recently in the 90s, it started in the 90s, and many of the famous results were just proven recently, led to the theory of O-minimal structures. They give a generalization of semi-algebraic geometry. So we use a lot of algebraic geometry, but this is kind of a more general framework which especially gets rid of many of the things which we like holomorphicity also plays no role there. Yeah. And if you want to read a little bit about this is some book which I can recommend, but there are also very good review articles. So now recall, what is the question? We want to ask the zeros of some function, which depends on this kind of, on these t's and on the fluxes. And in order that this has only finitely many zeros, then it's very clear that this function has to be special, right? It cannot be a general function, because you can easily cook up functions which do not have this property. For example, take the sine function of phi minus 1, and if you go close to phi to 0, this has infinitely many zeros, yeah, this function. Or you take this function here, and it also has infinitely many zeros. Even so, they kind of get squeezed smaller and in smaller and smaller regions. Yeah, and this was discussed long ago by Acharya and Douglas, this sort of function, and they tried to come up with arguments why they should not be fine and so on. But what one actually finds in this proof here is that these functions just never occur. Yeah, in these flux compactifications at least. So the theory of O-minimal structures gives a precise answer to what this special property is. Yeah. Now, I cannot give you in such a short time an introduction to O-minimal structures, but just to give you some intuition of what this amounts to. Well, on the real line, you can easily imagine what these finite structures are. So these are consisting just of finite number of points, finite number of intervals, and so on. And the tricky part is to extend this to Rn, to higher dimensional spaces. So the intuitive requirement is to include projections to R, which give this type of sets, and then allow for finite unions, intersection, products, and so on. And there is the general description of the structure. We don't have to read this in detail. I don't have time anyway. So the fact is, there is a well-defined definition, and it's a very powerful definition to extend this to Rn. It's a new way of doing topology. And then once you give this, then you can define what you mean by a tame function. Namely, a tame function is where the graph of the function is within this finite structure, or in this structure with these finiteness properties. And then you can prove remarkable theorems, for example, that such a definable function always has finitely many monotonic pieces. Yeah, so there is always kind of a finite decomposition, and then in between the function is monotonic or constant. Another consequence is if you have a function which is definable and holomorphic, it's just a polynomial, it's algebraic. The remarkable things is there are non-trivial examples of these structures. So that's where the story now really begins. Namely, there are non-trivial examples of these structures, and they are defined by what kind of functions you can add. And so you can add polynomials, okay? This is actually part of the definition of such structures. But you can also add real restricted real analytic function, and you can add exponential functions. And exponential function is crucial for us because, of course, we talked about essential exponential corrections. So the structure has to have the chance to include exponential functions. And in fact, there is a combined structure which has both analytic and exponential functions in it. And the period map, so the thing which I discussed before, is one of these definable functions. So then to close my talk, let me end with a conjecture. Now, given the success of understanding that the complex structure moduli space, the flux vacua, live in such a structure, in this abstract but restricted framework, it seems very natural to conjecture. Yeah, that's what we do in the swampland sometimes, to say, well, maybe the landscape in general is of this type. Okay, so I now combine the effective theories by recording their moduli space, rank of gauge group, matter spectrum, and so on. And I claim that the string theory landscape built out of this information is definable in this O-minimal structure. And all the coupling functions of the effective theory are actually definable as well in this function, in this structure. So they all respect these finiteness properties. And so finiteness is by no means just a yes or no statement. It actually constrains every function which you have in your theory. And this is, I think this is, if true, that would be remarkable. Yeah. So that brings me to the end. With the conclusions, we uncovered some structure of the complex structure moduli space using asymptotic Hodge theory. Well, the idea was that we don't have to scan through Calabi-Yau examples anymore. Then we argued that there is a new finiteness result. I didn't explain you the proof. Don't misunderstand me. I just gave you some hints. The proof is quite lengthy and technically involved, but it can be shown. And then I suggested to use this O-minimal structure to describe the string landscape in general. Thank you very much.
Thank you very much for the nice talk. Are there questions?
May I ask a quick question, maybe? So about this tame function again, just to, I'm not sure whether I got it right. So I'm trying to picture what it is actually. So you said like examples of this tame function is like analytic and exponential, or are you saying they are all that can happen here, or what exactly? I mean, I didn't get actually.
Yeah. So no, this is understandable because I'm always, it's very tricky to introduce this in such a talk, but I think the best way of thinking about a tame function is this kind of theorem which I recalled. So this is the best way of thinking of a tame function, namely, this is a proof. This is a theorem, right? This is a consequence of this tame function, that every tame function from R to R, or from some interval to R, can be split into finite can be split in a way that you divide the real line into finite number of intervals. And then on this finite number of intervals, the function is monotonic and continuous. So the function can be can have non-continuities. I don't know what's the precise English word, where it's kind of jumps, but only at finitely many places. So there are finitely many jumps allowed. Yeah, but in all the other places, it has to be monotonic and continuous. Or yeah,
but it does have a global expression as some.
It's a global statement. Yes, it's very important that it's a global statement. Yes, so you can write it down. These this is these are all the functions which can occur in these structures. Yeah.
Okay, thanks. Maybe I want to know more about it maybe later.
And that's, you see, a polynomial immediately satisfies this.
Sure, yeah.
Yeah, a polynomial immediately satisfies. The sine function doesn't satisfy this.
Yeah, infinitely many.
Right, because if you have infinitely many, like minima, if you want. And so it violates this theorem, so the sine function can never be a definable function. But if you cut off the sine and you just look at one period of the sine, it's definable. So it's a real analytic function, but it's restricted, and therefore it can be definable, and so on. So you see, it's a huge framework. Yeah, but if you combine these ideas with what we have, you find restrictions. So you see, I ruled out the scalar potentials, which Douglas et al. Discussed. They can never occur in these settings.
But why did it have to be a tame function to begin with? Sorry, maybe.
Say again?
Why did you? How did you know that the potential has to be a tame function again?
Well, for the complex structure moduli space, we show it, we prove it, and we prove it using. Of course, it's very difficult to prove this. You have to use these SL2 techniques because the tame. So now you have to check every period if you want. Yeah. And checking every period is what they did in their famous paper, right? They showed that the periods themselves are tame functions, and so they have very restricted properties. And please, I mean, the important thing is, of course, in the periods there are exponentials, and you might think, oh, there are sine functions coming in, right? They are the complex exponentials, so. Cosine and sine is not something which you would not come up as a string theorist.
Can I ask Can I also ask something very stupid? I mean, what goes wrong if there are infinitely many vacua? No,
well, nothing goes wrong per se, right? In the sense that they just certain like statistical arguments. You cannot make any statistical arguments in a meaningful way, for example, right? If you have infinitely many vacua and you say half of them have certain properties, that's meaningless, yeah. But of course there's no strict reason why this should be ruled out. Of course, you might also argue that kind of the predictability of string theory depends on how many vacua we have, right? That was the standard argument. If you have one, then there's a higher predictability. If you have infinitely many, then you might think that there's no predictable statement, which is not quite true because all of these infinitely many could predict the same thing. But okay.
But from the perspective of landscape, having infinitely many things will be a good thing, no? There are infinitely many.
No, this is the whole point. From my perspective, no. Yeah, I think from the perspective of landscape, it's important to have finiteness is a very important principle, and I promote it to the principle of the landscape now. Yeah. I mean, it's from what I say, yeah. I mean, this gives you it puts some predictable power into string theory, if you want.
Okay. Thank you very much. Okay. So if there are no more questions for now, let's thank Thomas again for the very nice talk.